Hello students, I welcome you all on the EduSet program. Today the topic of my discussion is aldehydes and ketones. The aldehydes and ketones, these are the two isomeric series, both of which contain the carbonyl functional group. This is the carbonyl functional groups. Aldehydes and ketones, they vary with respect to each other on depending upon the nature of these two substituents which are attached with the carbonyl functional group. If out of these two substituents one is the hydrogen, the compound is the aldehyde, and if both the substituents are the alkyl groups, then the compound is the ketone. If the second substituent attached to the carbonyl is the hydrogen, this is the first member of the series of the aldehyde, that is the formaldehyde, and if the other member is the alkyl group, this R can be the alkyl or the aryl group. These are the other members of the aldehyde series other than the formaldehyde. In case of ketones, the R and R dash, these can be both the alkyl groups or both the aryl groups, or one can be the alkyl and other can be the aryl group. In aldehydes, the functional group is the CHO, known as the aldehydic group. In case of ketones, the functional group is the C double bond O, known as the ketonic group. The ketones are further of two types, simple ketones and mixed ketones. This classification of ketones depends upon the nature of the alkyl substituents. If the two alkyl substituents attached with the carbonyl function, they are the same, then the ketones are known as the simple ketones. And if the two alkyl or two aryl substituents attached with the carbonyl function are different, they are known as the mixed ketones. In case of mixed ketones, one can be the alkyl group, other may be the aryl group, or one can be one alkyl group and the other may be the second alkyl group. So ketones are of two types, that is the simple ketones and the mixed ketones. Now coming to the nomenclature of the aldehydes and ketones, firstly we will take up the nomenclature of aldehydes. As we know, all the compounds can be named depending upon two systems. One is the common system, another is the IUPAC system. Firstly, we will take up the common names of the aldehydes. While giving common names to the aldehydes, these common names of aldehydes are derived from the common names of the corresponding carboxylic acids. We drop the word "ic" and add the word aldehyde. For example, like butyraldehyde is derived from the butyric acid. Ic acid of the butyric acid is replaced with the aldehyde, so name of the compound becomes butyraldehyde. Similarly, isobutyraldehyde from the isobutyric acid. Why this compound is known as the isobutyric acid and why this is known as the butyric acid? As we know, any compound containing the 4 carbon chain is the butane, and if it is having a aldehyde group, it will be the butyraldehyde. Why the word iso? Because the two substituents attached with one of the carbon, they are the same, that is why the name iso. So this compound becomes the isobutyraldehyde, or it can be named otherwise alpha methyl propionaldehyde. These are other examples of the aldehydes like benzaldehyde, orthotolvaaldehyde, orthotolvaaldehyde, from where this name has come. The benzene ring bearing the methyl and no aldehyde is known as the toluene group. Once one aldehyde group is attached to such type of ring, the name given to that compound is the toluealdehyde. Now the aldehyde group and methyl, they have ortho position with respect to each other, that is why the full name is orthotoluealdehyde. This is the first member of the series, that is the formaldehyde, and this is another example of the aldehyde, that is the phenyl acetaldehyde. This is the acetaldehyde moiety. This is the acetaldehyde moiety. One H of the acetaldehyde is replaced with the phenyl moiety, that is why the name phenyl acetaldehyde. Coming to the IUPAC names of the aldehydes. During the IUPAC naming of the aldehydes, first of all we will select the longest chain, longest continuous carbon chain containing the carbonyl function, that is the CHO function. Always the CHO group is numbered as 1, and we name the compound depending upon the name of the corresponding alkane. We drop the word E, we drop the alphabet E and add the word al, that is from butane it is butanol. This compound is 2-methyl propanol. This is named as 1, 2, 3, 2 position pe we have a methyl group, so this compound is named as 2-methyl propanol. This is the first member of the series. The common name for this compound is the formaldehyde, and the IUPAC name for this compound is the methanol. This is the second member, that is the ethanol. Then coming to the naming of the ketones. Firstly, we will take up the common names of the ketones. Commonly, the ketones are named as the alkyl ketones if the two alkyl groups attached to the carbonyl moiety are different, or they are named as the dialkyl ketones if the two alkyl groups attached with the ketone are the same. That is, this compound is named as ethyl methyl ketone and this compound is named as diethyl ketone. This is another example of the ketone, which is methyl N propyl ketone. That is, the ketone moiety is attached with one methyl and one N propyl group. So, the name of the compound is the methyl N propyl ketone. A special name is given to this type of the compound. This compound is named as acetone. Acetone is the common name of this compound. Now, there is one category of compounds in which the carbonyl group is attached to the benzene ring. This ring along with the carbonyl function is known as the O phenols. So, while naming this type of the compounds, we drop the word ic acid and add the word O phenol. For example, this compound is named as benzophenone. This compound is known as acetophenone. Now, taking the IUPAC nomenclature of the ketones. While giving the IUPAC naming to the ketones, firstly we select the longest continuous carbon chain containing the carbonyl group. Now, drop the word E of the corresponding alkane and add the word on. Assign number for the position of the carbonyl using the principle of lower number. For example, while giving IUPAC name to this compound, we firstly select the longest chain. This is a straight chain compound. Now, we number this compound so that the lowest number comes to the ketone moiety. So, we start numbering from this position 1, 2, 3, 4. So, this is the derivative of the butane. This compound is named as the 2-butane. Similarly, this compound is the 3-pentanone and this compound is the 2-pentanone. Now, coming to the synthesis of aldehydes and ketones, there are a number of methods for the synthesis of the aldehydes and ketones. The most important methods for the synthesis of the aldehydes are the oxidation of primary alcohols, whereas those of the ketone is oxidation of secondary alcohols. So, it is clear that primary alcohols upon oxidation gives the aldehydes, whereas secondary alcohols upon oxidation gives the ketones. The next method for synthesizing the aldehydes is the oxidation of methyl aromatics, and another method is the reduction of acid chlorides. For the synthesis of ketones, we take up the methods like Friedel-Crafts acylation, coupling of the dialkyl copper lithium with the acid chloride. So, these are the most important methods which are used for the synthesis of aldehydes. Along with these methods, we have certain other methods and we will discuss all the methods for the synthesis of aldehydes and ketones one by one. Firstly, we will take up the oxidation of primary alcohols for the synthesis of aldehydes. Here, the primary alcohol is treated with an oxidizing agent, forms the aldehyde. But the major limitation of this method is that once the aldehyde is formed, it is immediately gets oxidized to the carboxylic acid. To avoid this oxidation, the aldehyde is removed from the reaction mixture as soon as it is formed, because the aldehydes have the lower boiling points as compared to the corresponding alcohols. So, to avoid the further oxidation of the aldehydes to the carboxylic acid stage, the aldehyde must be distilled off from the reaction mixture. This slide shows the examples for the oxidation of primary alcohols. For example, 1-propanol upon oxidation with a mixture of potassium dichromate and sulfuric acid forms the propanol, and 1-butanol upon oxidation with potassium dichromate and sulfuric acid forms the butanol. So, alcoholic group gets oxidized to the corresponding aldehydic group. Here we can also see that the propanol, that is the aldehyde, is having the lower boiling point as compared to the corresponding alcohol. Similarly, the butanol is having the lower boiling point as compared to the corresponding alcohol. So, the aldehydes can be easily distilled off from the reaction mixture as soon as they are formed to avoid their further oxidation to the carboxylic acids. Or to avoid the oxidation of aldehydes to carboxylic acids, we can use also certain special oxidizing agents. One of the example of such an oxidizing agent is the Sarrett's reagent or Collins reagent. This reagent is formed by careful addition of chromium trioxide to excess of pyridine. So, chromium trioxide reacts with 2 moles of pyridine and forms the Sarrett's reagent, that is the chromic oxide pyridine complex. This complex in the presence of dichloromethane is used for the oxidation of the alcohols to the corresponding aldehydes. This method has the advantage that the aldehydes formed are not further oxidized to the carboxylic acids. Another example of the oxidizing agent which does not oxidize the aldehydes formed to the carboxylic acids is the pyridinium dichromate. This oxidizing agent is obtained by mixing pyridine, potassium dichromate and HCl in dichloromethane. This is 2 molecules of pyridine reacts with 2 moles of HCl plus 1 mole of potassium dichromate in dichloromethane forms the complex known as the pyridinium dichromate complex, and this is the oxidizing agent which is used for the oxidation of the alcohols to the aldehydes. Another method for synthesizing the aldehydes is the catalytic dehydrogenation of primary alcohols. The primary alcohols upon dehydrogenation in the presence of the catalyst undergo direct elimination of hydrogen and forms the corresponding aldehyde. For example, N-propyl alcohol when passed through heated copper tube at a temperature of 475 to 575 Kelvin, it loses a mole of hydrogen and forms the corresponding aldehyde, that is the propionaldehyde. The another method for synthesizing the aldehyde is the reduction of acid chlorides. This method is also known by the name Rosenmund's reaction. In this method, there is partial reduction of the acid chlorides. The reaction is stopped as soon as the evolution of HCl gas ceases, as it prevents further reduction of aldehydes into alcohols. During the Rosenmund's reaction, a mole of acid chloride is reduced, that is, it is treated with the hydrogen in the presence of catalyst, that is palladium, partially poisoned over barium sulfate. The acid chloride gets reduced to form the aldehyde and HCl. The limitation of this method is that the aldehyde formed can be further reduced to the alcohol. To avoid the further reduction of aldehyde to the alcohol, the further reduction of aldehyde to the alcohol can be prevented by stopping the reaction as soon as the evolution of HCl gas ceases. Example of the such type of reduction is acetyl chloride when treated with hydrogen in the presence of palladium barium sulfate, we get the acetaldehyde plus HCl. Benzoyl chloride when treated with hydrogen in the presence of catalyst, it forms the benzaldehyde plus HCl. Another method for the reduction of acid chloride is by the use of the lithium tritertiary butoxy-aluminium hydride. This catalyst does not reduce any other easily reducible group present in the molecule. For example, during the reduction of para-nitrobenzoyl chloride, this moiety is the benzoyl chloride. It is having a nitro group at the para position. That is why the name para-nitrobenzoyl chloride. Para-nitrobenzoyl chloride, when treated with this reagent, that is the lithium tritertiary butoxy-aluminium tritertiary butoxy-aluminium hydride, the acid chloride group gets reduced to the corresponding aldehydic moiety, but the second reducible group, that is the nitro group, remains as such. So, we get the compound para-nitrobenzaldehyde. Next method for synthesizing the aldehydes is the catalytic decomposition of carboxylic acids. That is, the carboxylic acids are decomposed in the presence of the catalyst. Any carboxylic acid other than the methanoic acid when treated with methanoic acid in the presence of catalyst manganese dioxide at a temperature of 573 Kelvin forms the aldehyde plus carbon dioxide plus water. For example, propanoic acid when treated with the methanoic acid forms the aldehyde propanol. Here the acid part of the propanoic acid is decomposed catalytically to the aldehyde part or is reduced catalytically to the aldehyde part and forms the aldehyde, that is the propanol. Next method for the synthesis of the aldehydes is the ozonolysis of the alkenes. Alkenes react with ozone to form ozonide, which is decomposed with a reducing agent. This is the alkene 1-butene. This is a butane compound having double bond at the 1 position. So, this compound is the 1-butene. When treated with ozone, it forms the ozonide, that is the ozone gets added to the double bond position. 1 oxygen molecule on the upper side and 2 oxygen on the lower side. So, this is the ozonide. This when hydrolyzed in the presence of zinc, the compound gets hydrolyzed to form the aldehydes. That is, one molecule is the propionaldehyde, another is the formaldehyde. This is the formaldehyde, the compound containing 3 carbon is the propionaldehyde. So, ozonolysis, from the ozonolysis of 1-butene, firstly we will get the ozonide, which upon hydrolysis forms 2 molecules of the aldehydes, that is formaldehyde and propionaldehyde. Next method is the oxidation of methyl benzenes. This is an example of the methyl benzene, that is toluene. This method is used for the preparation of aromatic aldehydes. Here the methyl benzenes are treated with chromium trioxide in acetic anhydride. Simple or substituted methyl benzene when treated with chromium trioxide in the presence of acetic anhydride, firstly it forms the arylidene diacetate. That is a compound in which the 2 acetate moieties are attached with the single carbon atom. This is also known as the geminal diacetate. This is an unstable moiety. This, as soon as this moiety is formed, this undergo hydrolysis to form the corresponding aldehyde and 1 mole of the carboxylic acid. For example, toluene upon treatment with chromium trioxide and acetic anhydride form the benzylidene diacetate, which upon hydrolysis forms the benzaldehyde and acetic acid. Then next method for the oxidation of methyl benzenes. One method for the oxidation of methyl benzene is use of the chromium trioxide in acetic anhydride. Another method for the oxidation of methyl benzene is with the use of the chromyl chloride or by the use of the manganese dioxide. The reaction in which chromyl chloride is used as a catalyst is known as the Itard's reaction. So, methyl benzene, for example toluene, when treated with the chromyl chloride, this is the structure of the chromyl chloride. It first forms a addition complex which upon hydrolysis forms the aldehyde, that is the benzaldehyde. Another method is the Gattermann-Koch reaction. This method is also used for preparing the aromatic aldehydes. One method for preparing the aromatic aldehyde is the oxidation of methyl benzenes. Another method is the Gattermann-Koch reaction. In this method, we treat benzene by treating benzene or other aromatic compound with a mixture of carbon monoxide and HCl in the presence of a Lewis acid like aluminium chloride and copper 1 halide like cuprous halide. So, a mixture of benzene, carbon monoxide and HCl when treated with a Lewis acid like aluminium chloride and cuprous halide or cuprous chloride, it forms the benzaldehyde plus HCl. So, Gattermann-Koch reaction is used for the synthesis of the aromatic aldehydes. Next method is the Reimer-Tiemann reaction. This method is used for preparing the phenolic aldehydes, that is the aldehydes in which there is one phenolic group. This method is used for preparing those phenolic aldehydes, particularly those in which the aldehydic group is present in the ortho position to the phenolic group. In this compound, the aldehyde group is present at the ortho position to the phenolic, that is the salicylaldehyde, which is the main product, whereas the para-hydroxybenzaldehyde is also formed because the hydroxy group is ortho-para directing. So, the incoming aldehyde group comes to both positions, that is the ortho position and the para position. In this, the ortho product is the main product, whereas the para product is formed in small quantities. So, when phenol is treated with chloroform and sodium hydroxide at a temperature of 333 Kelvin, it forms two products. One is the ortho hydroxybenzaldehyde and the other is the para hydroxybenzaldehyde. The special name for the compound ortho hydroxybenzaldehyde is the salicylaldehyde, which is the main product, and the second compound, that is the para-hydroxybenzaldehyde, is formed in small quantities. Now, from where the word para and ortho, if the two substituents are present at a position 1 and 2 with respect to each other, then the word ortho is used, and if the two substituents are present with respect to each other on the position 1 and 4, then the word para is used. Next method for the synthesis of the ketones is the oxidation of the secondary alcohols. Now we have till now we have discussed the synthesis of the aldehydes. We have discussed various methods for synthesizing the aldehydes, that is the Reimer-Tiemann reaction, Gattermann-Koch reaction, oxidation of methyl benzene, ozonolysis of the alkenes, catalytic decomposition of carboxylic acids, reduction of acid chlorides, and catalytic dehydrogenation of primary alcohols. And the very first method for the synthesizing the aldehyde is the oxidation of the primary alcohols. After discussing the methods for the synthesis of the aldehydes, now we will discuss the various methods for synthesizing the ketones. The first method for the synthesis of ketone is the oxidation of secondary alcohol. Now, the secondary alcohols can be oxidized by the use of acidified sodium or potassium dichromate or potassium permanganate or chromium trioxide in a variety of solvents. For example, this is a secondary alcohol. Now, why the word secondary? Because here the alcoholic group OH group is attached to a carbon which is further attached with two alkyl groups. So, carbon bearing two alkyl groups and one hydrogen is the secondary carbon, whereas carbon bearing two hydrogens and one alkyl group is the primary carbon, and the carbon bearing all the alkyl groups without any hydrogen is known as the tertiary carbon. So, this is the secondary carbon. So, the name secondary alcohol. Secondary alcohol upon oxidation in the presence of potassium dichromate sulfuric acid forms the corresponding ketone, that is this CHOH moiety loses a mole of hydrogen and we get a ketonic moiety instead of the alcoholic moiety. For example, secondary butyl alcohol upon oxidation forms the methyl ethyl ketone, that is methyl ethyl ketone. Here R and R dash can be both alkyl, can be both aryl, or one can be alkyl and another can be aryl. The next method for synthesizing the ketones is the catalytic dehydrogenation of secondary alcohols. Firstly, we have discussed the oxidation of secondary alcohols. Next is the catalytic dehydrogenation of secondary alcohols, that is removal of hydrogen in the presence of a catalyst. So, secondary alcohols when treated with a catalyst or when passed through a hot copper tube at a temperature of 475 to 575 Kelvin, they lose a molecule of hydrogen 1 and 2. So, they lose a molecule of hydrogen and this alcoholic moiety is oxidized or dehydrogenated to the ketonic moiety. So, secondary alcohols upon dehydrogenation forms the ketones. Moreover, the secondary alcohols upon oxidation also forms the ketones. The example is isopropyl alcohol upon catalytic dehydrogenation forms the corresponding acetone plus hydrogen. Now, next method for preparing the ketone is the reaction of nitriles with Grignard reagent or organolithium compound. This is the Grignard reagent, alkyl magnesium halide. This is the nitrile compound, that is a compound containing the CN group is known as the nitrile compound or the cyano compound. Nitrile compound upon treatment with Grignard reagent in the presence of ether firstly forms the addition product which upon hydrolysis in the presence of the acid forms the ketone. This addition product breaks from this position, the oxygen comes to the this moiety and this moiety is lost as ammonium ion and magnesium ion. Similarly, the nitriles when treated with alkyl lithium in the presence of ether firstly they form the addition product which upon hydrolysis forms the ketones ammonium ion and lithium. Next method is reaction of acid chloride with organic cadmium compound. So, acid chlorides when treated with organic cadmium compound, that is dialkyl or diaryl cadmium, form the ketone plus cadmium chloride. For example, benzoyl chloride upon treatment with dimethyl cadmium forms the acetophenone. Benzene ring of this, CO of this remains intact. This chlorine from benzoyl chloride is lost and cadmium from this dimethyl cadmium is lost and we get the acetophenone. Next method is the Friedel-Crafts acylation. This is used for preparing ketones in which ketone group is attached to at least one aromatic ring. So, one of the alkyl group attached to the ketone moiety is the aromatic ring in case of the Friedel-Crafts acylation. Any aromatic compound when treated with the acid chloride in presence of anhydrous aluminium chloride, it forms the acetone plus HCl. Here R can be a alkyl group or the aryl group. This is Ar is the aromatic, this R can be the alkyl or the aryl group. For example, benzene when treated with acetic anhydride in the presence of anhydrous aluminium chloride forms the acetophenone. But when benzene treated with benzoyl chloride in the presence of anhydrous aluminium chloride, it forms the benzophenone. But if we react with the a benzoyl chloride moiety with a benzene ring which is having a nitro substituent, nitro is a deactivating substituent, then no reaction occurs in the presence of aluminium chloride. Thus, Friedel-Crafts acylation does not work on deactivated rings. Only the simple rings or the activated rings can undergo Friedel-Crafts acylation, whereas deactivated rings, they does not undergo Friedel-Crafts acylation. This is the mechanism for the Friedel-Crafts acylation. Carbonyl carbon is electron deficient. This attacks the electron rich aluminium chloride moiety, forms the carbocation. This carbocation attacks the benzene ring or the aromatic ring. It is the rate determining step and forms a benzene carbocation moiety, which is a resonance hybrid of 3 contributing structures. This benzene carbocation is from this benzene carbocation, the aluminium chloride with a negative charge abstracts a proton, and this bond goes to the benzene, forms the corresponding ketone plus HCl plus aluminium chloride. Now, next method is the hydration of alkynes. Alkynes upon hydrolysis in the presence of mercury sulphate and sulfuric acid first forms the enol type of compound. This undergo tautomerism to form the ketone. So, this is the enol ketone, keto-enol tautomerism. So, 2-butene firstly forms the enol compound, which upon tautomerization forms the ketone compound. That is, from 2-butene we get the methyl-ethyl ketone. Next method for synthesizing the ketones is the ozonolysis of the alkenes. Alkenes upon treatment with ozone first form the ozonide, which upon hydrolysis in the presence of zinc forms the ketone. That is, from 2,3-dimethyl 2-butene we get the ketone acetone. Now, the last method for synthesizing the ketone is the acetoacetic ester synthesis. This method is used for preparing the methyl ketones. Acetoacetic ester, this is the aceto moiety, this is the acetic ester moiety, ethyl acetoacetic acid. If we see this central compound CH3COOH will be the acetic acid, the H of the acid is replaced with the ethyl acid, ethyl acetic acid. Now, one H of the methyl moiety is replaced with the acetyl moiety, aceto. So, the name of this compound is the acetoacetic ester. This compound when treated with the sodium salt, sodium ethoxide, first form the sodium salt of the acetoacetic ester, which upon treatment with the alkyl halide form alkyl acetoacetic ester. Upon treatment with the base hydroxide ion, it forms the carboxylate moiety, which abstracts a proton, forms the alkyl acetoacetic acid, which upon heating forms the ketone, undergo decarboxylation, form the corresponding ketone plus carbon dioxide. This COH moiety, that is the acid moiety, is lost as the carbon dioxide moiety, and we are left with the ketone, that is the methyl ketone. So, this is all about the synthesis of the ketones. We have discussed various methods for synthesizing the ketones. Now, after discussing the synthesis of the aldehydes and the synthesis of the ketones, next we will discuss about the reactions of aldehydes and ketones. The most important reactions of the aldehyde and ketones are the oxidation reactions, reduction reactions, and nucleophilic addition reactions. So, both aldehydes and ketones undergo oxidation, reduction and nucleophilic addition reactions, but the nature of product will vary depending upon the starting compound, that is whether the starting compound is the aldehyde or it is the ketone. Aldehydes are, if we compare the reactions of aldehydes and ketones, the aldehydes are easily oxidized whereas ketones are not. Moreover, the aldehydes are more reactive in nucleophilic addition reactions as compared to the ketones. So, if we see aldehydes and ketones, upon reduction they may form the alkanes, or upon reduction they may form the alcohols. Upon oxidation they form the carboxylic acids, and upon treatment with the nucleophilic reagents they form the nucleophilic addition products or the addition products. Now, we will firstly we will discuss the nucleophilic addition reactions of the aldehydes ketones. After that we will discuss the reduction of aldehyde ketones, and lastly we will discuss about the oxidation of aldehydes and ketones. So, firstly taking the nucleophilic addition reaction.